talk to you about pentameric ligand-gated ion channels. So actually I worked, as mentioned, in Jean-Pierre Change's laboratory decades ago. Pasteur Institute is actually a place where the first neurotransmitter receptor was purified. It was in the 70s, last 70s. And in the 90s I went to Jean-Pierre's laboratory working as a biochemist, trying to understand what's happening in these proteins and how it works, and how neurotransmitter binding promotes channel opening and ensures synaptic transmission. So this is for the historical background. And for a long time, the 3D structures of these receptors was not known, such that it was really difficult to understand really the molecular mechanisms. So my talk will be dedicated more to the post-structural aspect of this receptor. The first key structure was done by Nigel Unwin. It was at the beginning of the century. It was by cryo-electron microscopy, and it was at medium resolution. And then the first high-resolution structure were performed thanks to the discovery of bacterial ancestors of nicotinic receptor. This is where I contributed to the field. So actually nicotinic receptors so far are found only in animals in the eukaryotic kingdom. And homologs of this receptor were found in several bacteria, including Proteobacteria, Cyanobacteria. And in my group, we were first to isolate one of these prokaryotic ancestors from the Cyanobacteria Globacter violaceus. And it was one of the first structures published in the family of pentameric ligand-gated ion channel.
Where is it? Is it your computer?
It is my computer.
I look
You look for the presentation?
Our assistant has not yet come, but I propose that to make our speaker life easier. He keeps his computer, shows, it helps him to tell you, and then he shows the computer to the audience, and those with a good I see, can recognize some details. So I cannot offer another solution that to see.
I will stay. I will stay with this lecture.
Yeah, this is excellent. Peter will be staying. Excellent. Yeah.
It will be a bit complicated.
Okay.
Qu'est-ce que c'est possible? It's not possible yet.
Why? It's possible.
So let's try. Give me 10 minutes, but I won't be able to.
I can finish.
Yeah. Just
relax.
it's a nice experience. Just to check. I don't know when they make it.
Yeah, so this is because now the 3D structure of these receptors is being more and more known, and following the work on the bacterial ancestors, many receptors have been solved at atomic resolution, including that of C. elegans receptor, the UCL, and more recently mammalian receptor. We know the structure of the 5-HT3, of the glycine receptor. So we know more and more about the structure of these receptors. But still, my lab is working on the bacterial ancestor as a model for the whole family. So our idea is not really to understand really how nicotine acts or acetylcholine acts on this receptor, but we want to understand the precise mechanisms that are common to the whole family of pentameric channel receptors. So the bacterial receptors are still very interesting models because they are relatively easy to produce. You can screen a lot of crystallization conditions, you can make a lot of biochemistry, and so you can make a lot of biochemical experiments.
You know the endogenous ligand?
So that's a very good question. So this receptor we work with is called GLIC. It's a receptor from Globacter violaceus. And we found that it's activated by protons. So if you decrease the pH from 7 to 5, you will get very robust current in cell lines in oocytes. So this is an agonist, but it's not a molecule. And we don't know whether this proton is an endogenous activator in the bacteria. So we have no idea of the physiology of this receptor, but we can activate it with proton. It gives with a pH 50 around 5, and we can show single channel recordings. So this is our way to activate this receptor. And so we made some crystallography of this receptor, and we were lucky enough to find conditions for crystallization at pH 7 in the resting conformation and at pH 4 in the activated conformation. So we have the two forms, closed channel and open channel. And based on these two structures, we propose the first atomic resolution activation mechanisms of a member of the family. So I have 5 fingers, so we try to show you. So you see these receptors, and actually in the resting conformation, the subunits are far apart. And when you decrease the proton concentration, you have a compaction of the whole extracellular domain. The ECD comes closer together, and this is concerted with an opening of the channel in the transmembrane part. So this is really, roughly, what we see by X-ray crystallography. And what I wanted to talk to you today is our recent experiments in the lab, because our concern is that crystallography is made in very artificial conditions. So if you want to make a structure of the protein, you have to extract the protein from the membrane using detergent, and then you crystallize the protein, which means in 3 dimensions the protein interacts with many neighbors, and so the condition is very artificial and very far from the physiology. And so we wanted to have structural data in membrane, in lipidic membrane, and in real time. And for this, to this aim, maybe I can go there. So there was beautiful movies, I'm sorry.
You can show the movie.
Look at the form.
And so to this end, we developed a new methodology using fluorescence. So the idea is from the X-ray structure, the change in conformation are very small, are very subtle. So you have a change in subunit interaction, you have an opening of the channel, but the movement are very small in amplitude. And so to follow this movement, we use a fluorescence quenching approach. So the idea is that on the protein you add a cysteine somewhere, and you react to cysteine with a biman, which is a very small fluorescent dye. And on other part of the protein, you introduce either a tryptophan or a tyrosine. And so both the tryptophan will quench the biman fluorescence when the two residues are in contact. And so you can follow local organization of the protein. If during the global organization it goes to contact, you have a strong quenching of the fluorescence. And so we used Glick. We did a mapping of many regions, especially the extracellular domain at the subunit interface and the upper part of the channel. And we developed 5 what we call allosteric sensors of the protein conformation. And so these sensors show that upon pH drop, you have indeed a compaction of the extracellular domain. So the two subunits come closer together. And we show also that the key loop at near the channel gate goes outside from the channel, which is considered with channel opening. And so we have all these sensors. So we show that in detergent, apparently the motion of the protein freely moving is similar to the motion of the protein we see in crystals. But using this fluorescence tool, we further go to lipid environment, so we reconstitute the protein into liposomes. We show that its motion are essentially conserved in liposomes. We perform also some rapid kinetic experiments, and this was quite unexpected because we show that this motion occurred with very fast kinetics. In less than 1 millisecond, all the motion are completed. However, we know that this is a rather slow activated channel within the family, and it takes 10 to 50 milliseconds to activate. And so our experiments identify a pre-active conformation. So the receptor is at rest. When you drop the pH, you have this contraction of extracellular domain, movement of the loop, but the channel is still closed. So this is very fast, and then you have a slower motion, which is a local opening of the channel. So this is really the story I wanted to share with you. This is under review. And this notion that you have intermediate conformation in the pathway of activation of this receptor was already proposed for eukaryotic receptor, notably for nicotinic and for glycine receptor, thanks to kinetic analysis on single channel recording, mainly by Paul Kuhn, C. Vilotti, Auerbach, Stevenson. And our work proposed a structural characterization for such an intermediate on a model bacterial receptor. So I think this is the story I wanted to tell you.
I can tell you.
Sure.
I give you 5 extra minutes from my talk. It will be very short.
Okay,
Yeah,
I'm
just
done.
well, as you like. Yeah, as you like.
But tell me please, how did you estimate this 1 millisecond time? So it's so rapid.
So it was by stop flow analysis. So we stop flow. So we took the glyc.
Yeah.
We made rapid mixing with proton, and then we followed fluorescence by stop flow kinetics. And so the change in fluorescence were in the dead time of the apparatus, which is 2 milliseconds. So we can say it's faster than 2 milliseconds. So we have some preliminary experiments by Tijan, where in Tijan you can resolve very fast kinetics that it is in the millisecond time range.
Yes, please, Israel.
The second stage, you say, the channel opening is 50 milliseconds.
Around, yeah.
And this is based on the natural physiological role within the bacterium.
So the 50 millisecond is based on the outside-out patch clamp recording, so it's really the fastest application you can have. We have no clues about the physiological role of glyc in bacterial functionality.
This is about the order of magnitude slower than the glyc receptor, right?
Sorry?
This is about the order of magnitude slower than the glyc receptor.
Yeah, it's much slower, yeah. Nicotinic receptor is millisecond activation, yeah. So it's much slower. So maybe the bacteria, that's right, maybe the bacteria don't need a very fast channel. It's not a synaptic channel, so maybe it doesn't need the channel to
Evolution is on that side.
Sorry?
Evolution is on that side.
Yeah, that's right.
Well, maybe the last short question, because we are slightly out of time, because we didn't try all the projectors yet around the building. So, very short question and short answer. Okay, Sasha?
All right. So my question is about the relation between bacterial pentameric receptors studied by you and the ample data, structural data on eukaryotic pentameric by Eric Bohr.
Yeah.
So do those sets of data really relate to each other?
Yeah, so you have really a common theme. If you compare, for example, so you have 3 sets of data, one for glyc, one for the glucial receptor from CNRS elegans, and one for the glycine receptor from human, I think. Which, for each you have 3 states, and you can propose activation mechanisms. So really the general trends are the same. So you have the compaction of the extracellular domain, and you have a tilt of the M2 helix to open the pore. So in the free system, it's really very well conserved. But if you look at the detail, there are important differences, especially at the transmembrane domain, where in glyc you have a more local change in M2 in the channel, whereas for the gluciate glycine receptor you have more profound organization of the transmembrane domain. So I think at this stage we cannot say really why those differences, because there may be 2 major regions. One reason would be maybe in the different structure, different allosteric states were captured, or maybe indeed different species gate in a different manner locally. And to answer this question, my feeling is that we need to accumulate much more structural data. The more structural data we have on the family, the more we will understand the transduction mechanisms, but also the difference between different species. Yeah.
Thank you very much. Unfortunately, we don't have more